Okay, welcome to Module 5, Functions. We finally got out of Module 4. We were there for a long time. And Lesson 1 is Concept of a Function. And it's going to seem like we're doing somewhat similar things as we did before. And that's okay. This is a really central area of math. And it's going to be really important for you all through high school. So let's look at concept of a function. Okay, so today in lesson 1, some of the key concepts are that a function, and we're going to define what that is a little later, a function allows us to make predictions about the motion of an object. Okay, that would just be one specific type of function. There are all types of functions where we can make predictions about maybe the height of a person or some other measurement of something. So a function will allow us to make predictions like that. But in this lesson, we're going to specifically talk about the motion of an object. And that should be familiar to you. We did a lot of that in science at the beginning of the year. So a lot of this is going to seem a little familiar. We're also going to talk about average speed again. And average speed can be calculated over a specific time interval. And we're going to be looking at that. And we've found out that constant rate, when you have a constant rate, the average speed never changes. But constant rate can't always be assumed. So one thing that we'll need to do with these functions is to check the average speed to see if it's the same all the time. Then we know that it's a constant rate, and that would be a linear function. Otherwise, it's something other than linear. And so we'll be looking at both of those. Okay. So you have this example 1 in your class notes. So we're going to look at that now together. Okay, so suppose a moving object travels 256 feet in 4 seconds. Assume that the object travels at a constant speed. That is, the motion of the object is linear and it has a constant rate of change. We are asked to write a linear equation in 2 variables to represent the situation and use it to make predictions about the distance traveled over various intervals of time. Okay, so we know that our object travels 256 feet in 4 seconds. Okay, and we're told down here, if we look down here, we're going to use x to be the number of seconds. And remember, we've said we always have the horizontal axis be time if time is one of the variables. And in this case, it is. So we can go 256 feet in 4 seconds. And in general, we will go y feet in x seconds. Okay, and remember, the only reason that we can know that these speeds are the same is because when we have constant speed, both of these are average speeds, right? The average speed over 4 seconds, the average speed over 6 seconds. But in a constant, when there's constant speed, the average speed is always the same. It's equal to some constant, some number. Okay, so if we have that, let's get rid of all the extra stuff there. We have this relationship, and if I take and, let's get a different color here. If I take and multiply both sides of this equation by x, then I can rewrite this as looking more like a linear equation that we're used to. So let's rewrite that. It would be, that would become 1. So we would have y is equal to 256 over 4 times x. And that would be my linear equation. And I would have y is equal to, if I simplify this, I'm going to get 64x. So what does that mean? I know that I can put in any number for time, and this linear equation will give me the distance in y. So if I put in 1, then I will have gone 64 feet. If I put in 2 for x, 2 times 64 is 128. And if I put in 3 times 64 would be 180 plus 12, 192. And I already know 4 seconds, 4 times 64 is 256. Now, if I wanted to calculate the average speed over the first 3 seconds, I could say that the distance was 192. Average speed is total distance over total time over 3 seconds. And when I divide that out, I'm going to get 64 feet per second. Okay, so the average speed is always the same over every time interval. Okay, so we said that the important thing about a function, or one of the important things, is that we can make predictions about the distance traveled over various intervals of time. So you might think about what are some predictions that we could make about the motion of this object. So you might be able to say that in 2 seconds, this object's going to travel 128 feet. You know, I might even go beyond and try to predict how far this object will travel in 5 seconds or 10 seconds. In 10 seconds, our object's going to travel 640 feet. So we could make some predictions like that. Okay, so let's look at example 2 now. The object, a stone, is dropped from a height of 256 feet. It takes exactly 4 seconds for the stone to hit the ground. How far does the stone drop in the first 3 seconds? What about the last 3 seconds? Can we assume constant speed in this situation? That is, can the situation be expressed using a linear equation? Okay, so here's a little bit more information now. So in example 1, we had the same numbers, but we assumed constant speed. So with a falling object, can we assume constant speed? So you may remember a little bit from 8th grade science, the beginning of the year, force and motion, about this topic, whether we can assume constant speed or not. There's a couple videos on the playlist that you can watch. There's a 10-second one called Ball Drop. Watch it a couple times and see what you can notice about the motion of the ball as it drops from the top of a building. And then there's another fun one that shows a vacuum chamber and falling objects. And see if you can see if it's constant speed there as well. So go ahead and pause the video and think about this question, and then come back and we'll get a little bit more information going here. Okay, so if this situation is linear, if it is constant speed, then we would know that in 3 seconds we would have 192 feet of drop. Okay, and so here's the actual data for that ball drop. So let's look at what's going on here. What does this show us? It shows us that in the first second, the ball drops 16 feet. And then by t equals 2 seconds, the ball has dropped 64 feet. So remember from our first data table, the ball dropped 64 feet in the first second, you know, just in 1 second. So at time t equals 2, the ball is at 64. T equals 3, the ball is at 144. And at t equals 4, the ball has hit the ground, 256 feet. down. Okay, so before we knew this additional information about the object, we made a prediction that, for instance, in 2 seconds, it would travel, what was it, 128 feet. And so now we know that that prediction was wrong, given that we have more information. So we didn't make an accurate prediction by assuming constant speed. So saying that a different way, since our predictions were incorrect, and this is actually what happened to the ball, then our assumption that the speed was constant was wrong. Okay, so let's see if we can organize this data into the table. So we can put the data that we have in our table. So in 1 second, the stone traveled 16 feet. In 2 seconds, it was down to 64 feet distance traveled, and then 144, and finally the 256 feet at 4 seconds. Okay, so what are some predictions that we could make now based on what we have? Well, we could say that after 1 second, at x equals 1, the stone dropped 16 feet. So we could say that. We could say in 3 seconds, it traveled 144 feet. But what if we wanted to make a prediction about 3.5 seconds? Where is the ball at 3.5 seconds? How would we have done this in the past? Like with a linear situation, what would we do? So think about that for a second, and then I'll write some things. Think about how we would predict where that ball would be in 3.5 seconds. Okay, so if we tried to do some work like we did before, like we said, well, if the ball travels x, not x, let's use a better variable here. If the ball travels y feet in 3.5 seconds, then we could set that equal to the ball traveling 16 feet in 1 second. And then we could solve for y. So we could solve for y by multiplying both sides by 3.5. And we would get that the distance y would be equal to 3.5 times 16, which would be 56. Okay, so using that model for prediction, we get that in 3.5 seconds, the distance traveled would be 56 feet. But that doesn't seem reasonable at all, does it? Because we know that it has to be more than 144. Because we know that in 3 seconds, it went 144. So it's got to be more than that. So this, using a proportion of constant rate didn't work. We could even do it again. We could look at the rate over the 3 seconds, say. So it went 144 feet in 3 seconds. So maybe it'll go y feet in 3.5 seconds. So again, we can multiply by 3.5 on both sides. And get that y equals, and I want 3.5 times 144 divided by 3. And if you work that out, you're going to get 168 for y. Yeah, for the distance traveled. So it would drop 168. Now that seems a little more reasonable, right? At least it's between 144 and 256. So let's do some more checking to see if this prediction is correct. But before we even go there, let's think about, do we trust the method that we use to get this prediction? Because the method didn't work at all using 16 feet in 1 second. So why would we expect the same method using 144 feet for 3 seconds work to be a good predictor of where that stone is going to be in 3.5 seconds? So that's one thing to think about. Our method doesn't seem reliable, even though our answer seems to somewhat make sense. Okay. But we have more information. So suppose we repeated the experiment and got this data. So now we know that in half a second, now we know these half-second intervals here. So we know that in half a second, it traveled 4 feet and down this table. So you can study the data here. In 3.5 seconds, it went 196 feet. So our method was predicting 168, not 196. So we were off. And so we have this, this additional data is going to help us make better predictions. So now we can make predictions down to the half second now, right? So we could know that in 2.5 seconds, our stone will have dropped 100 feet. But what if we wanted to know in 1.25 seconds? We don't have that information. So even though we have every half second here, what's happening with the stone, what if we needed to know every 1/10 of a second, or even more accurately than that? So this is actually, if you think about it, this is how functions are used in real life. If think of the space program, they want to know where that spacecraft is every second, every fraction of a second. We need to know things. We need to know the whole story. So this table tells us a lot of the story, but it doesn't tell us the whole story. And the whole story we want to know is for every time t between 0 and 4, for every number that falls between 0 and 4 for time, we want to know where that ball is, or that stone. It's a stone right now. And that would tell us the whole story. So only a function can do that. And that's what we're going to look at now. Okay, so now I'm going to ask you to just carefully look through exercises 1 through 6 and answer them, answer the questions. It's going to guide you through really sort of analyzing the data in this table, this most recent one that we've looked at. And by the time we get through to exercise 6, we're going to be looking at patterns in this data to see if we can tell something about the function that would give us the whole story. Okay, in lesson 2 of this module, we'll look at the function directly. But for now, we want to just really look at this data and see what we can find. So you're going to start by making some predictions like we were doing earlier. predictions that you could make from this table, and some that you couldn't make. Number 2 says predictions that would require more information. In number 3, you're going to start calculating average speed for different intervals. And so just this is the formula for average speed, right? It's your total distance traveled in a given amount of time divided by the time interval. So however far I went in 3 seconds divided by 3 would give me my average speed. So you're going to be doing that over different intervals. So you're going to look at how many feet did the stone drop in the first second, between 0 and 1 seconds, between 1 and 2, and so on, and comparing those. So we're looking for patterns, right? We're looking at data and looking to see what we can discover. And so number 5 will take you into that even more deeply, into the half-second intervals. And then finally in number 6, we're going to look for a pattern. Okay, so that's kind of an overview of exercises 1 through 6. So I'm going to let you go as far as you feel comfortable, and then come back and we'll check it together and talk about it a little bit more. Okay, so as far as predictions that you could make from this table, there are several. You could, any half-second interval, we can know how far this stone traveled. So I could say in 3.5 seconds, the stone will travel 196 feet. So anyway, we're just supposed to make 2 predictions like that. And then for predictions that would require more information, it might be, at 0.25 seconds, how far has the stone traveled in the first quarter of a second? Our table doesn't give us that information, so we've found that our methods for predicting that are unreliable because this doesn't appear to be a linear model. Okay, so predictions that we can and can't make. Okay, so let's look at number 3 then. What is the average speed of the object between 0 and 3 seconds? So let's look at the average speed. So since it's the total distance traveled divided by the time interval, we would have that the average speed would be equal to, going back to our data table, at 3 seconds, it's traveled 144 feet. So we've got 144 feet in 3 seconds. And that simplifies to 48 feet per second. 48 feet per second. Okay. So now we're asked, how does this compare to the average speed calculated over the same interval in example 1? So let's go back and look at example 1. Okay, so here is our function for example 1. So remember that we found that our assuming constant rate, the speed of this object would have been 64 feet per second. So that's different from what we got just now. Okay, so we could say something like in example 1, where we were assuming constant speed, example 1, the average speed was 64 feet per second. Okay, so looking at 4, we're gonna dive into this and dissect it down a little bit closer. So between 0 and 1, how many feet did the stone drop? in between 0 and 1 seconds, it dropped 16 feet. Okay, and how many feet did the stone drop between 1 and 2 seconds? So be careful on this one because it doesn't say between 0 and 2. It says between 1 and 2. So we want to look back at that, at our table that we're supposed to be using for exercises 1 through 5. At 1 second, it was at 16. And then at 2 seconds, it was at 64. So what I need to do is take 64 and subtract 16. So 64 minus 16 is 48 feet. Is that right? Okay, so in the interval between 1 second and 2 seconds, the stone traveled 48 feet. So it went a lot further in the second interval than in the first, right? In that second. Okay, how many feet did the stone drop between 2 and 3 seconds? So we need to go back to our data table. At 3 seconds, it was at 144, minus at 2 seconds, it was at 64. So it traveled an additional 80 feet in that interval. How many feet did the stone drop between 3 and 4? Well, at 4, it was at 256, and at 3, it was at 144. If I subtract those, I'm going to get 112. 112 feet. So in the first second, we dropped 16. And then the second, 48, the third second, 80, and then 112. So E says, compare the differences the stone dropped from one time interval to the next. What do you notice? Okay, so there's a couple things you could have noticed. The first one would be, probably the simplest, is that the numbers are getting bigger. It's dropping more feet for every second, for every additional second. Let's say that for every additional second. Oh, it's hard to write with this pen. Okay. Okay, and I'm going to grab a different color here and see if you noticed, maybe you noticed something even more. If I take 16 plus 32, I get 48. And if I take 48 plus 32, I get, that's right, 80. And if I take 80 plus 32, I get 112. So that's pretty cool. So not only is it dropping more feet, it's dropping an additional 32 each time. So over so I'm just going to put it right in here. So it's dropping 32 more feet for every additional second. So that's kind of a cool pattern if you notice that. That's pretty interesting. You might have just noticed that it was increasing. And that's okay, but it is 32 feet, and that's going to be important. All right, let's look at number 5. Now we're going to look at these half-second intervals. What is the average speed of the stone in each interval, 0.5 seconds? For example, the average speed over the interval from 3.5 to 4 is the distance traveled divided by the time. So here's an example here. 256 minus 196 over 0.5. So where did we get those numbers? Let's go back to our table. Here's the 256 right here minus 196 over that half-second interval. Okay, so that was 120 feet per second. So you want to repeat this process for every half-second interval. So 0 to 0.5, 0 to 0.5, 0.5 to 1, and so on. All right, so let's look at the results. You've already done this, of course. Okay, so here's the completed calculations that you should have obtained here. So in the first half second, the stone drops 4 feet. Divide that by the half-second time interval. We get 8 feet per second in that first interval. Then it goes up to 24 feet per second, up to 40, to 56. So see if you notice how much it's increasing each time. 56 to 72, to 88, and then to 104. Okay, so what you should notice there, when we compare the average speed between each time interval, okay, so in each half-second time interval, the speed increases by what? By 16 feet per second each time. So when we were at 72 feet per second, we add 16, we get 88. So for example, there's our example right there. So when that happens, you can check it at every time interval. It's always increasing by 16 feet per second. Every half second, it increases that much. Okay, so let's look at number 6. So number 6 is asking us to look for a pattern in the data of the falling stone. So in the first second, we've got 16. And this is just the data from the table in example 2. Then 64, 144, and 256. So you can just record your thoughts on this, and we're going to talk about it more in in lesson 2. So this is just sort of an open-ended one for you to just notice whatever patterns you see in this data and see if you can tell maybe what the function is going to be, although you don't need to figure that out. Okay, so after you've done that, let's talk about the lesson summary. So we have talked about the fact that functions can be used to predict real life situations, and that's exactly what they're for. And sometimes they are exact data, kind of what we saw in this lesson. We used actual data of falling objects. So they're used to make predictions in real life situations, and a function will allow us to predict the distance an object has traveled for any given time interval. So that's just one example of a function. There are many, many different kinds of functions. So we saw that constant rate, and we've talked about this in Module 4 too, we can't always assume constant rate. A lot of times constant rate even though it's not actually what's happening, is good enough to be a good predictor, but it wasn't in this situation, not with falling objects. It didn't give us good predictions at all. So if you look at the average speed over different time intervals, if those change, if that average speed changes, then you do not have a constant rate. And you do not have a linear function. So if the rate is changing, if the speed is changing, you don't have a linear function. Okay, so what I'd like to do is maybe help you out a little bit with the exit ticket. You can do the exit ticket now, and then I'm just going to discuss it briefly, discuss the results briefly before you go on to the problem set. So go ahead and grab your exit ticket now. You can either correct it with the book, or you could come back and finish the video and correct it that way. Okay, so you're given this graph, and this is a graph of a ball bounce. And so the x-axis is showing us the time. This is one bounce. So our time interval here is between 0 and 1 second. So at time 0, it hits the ground, bounces up, and back down in 1 second. At half a second, it's hit its highest bounce, and that's 4 feet. Okay, so you were asked to identify the height of the ball at the following values. So at 0, when t is 0, then the height is 0. And I'm going to write these as ordered pairs. You could have just written it out however, whatever you had room for. When t is 0.25, so at a quarter of a second, what I want to do is follow this up here and see that the ball is at 3 feet at 0.25 seconds. At 0.5, the ball's at its highest, which is 4 feet. At 0.75, the ball is coming back down, so it's at 3 feet. And then at 1 second, the ball's back down to the ground at 0. Okay? So we're asked to find what is the average speed of the ball over the first 0.25 seconds. So the average speed is going to be the distance traveled, which is 3, or 3 minus 0. It went from 0 up to 3 over 0.25. Okay, so this is equal to 3 divided by 1/4 is the same as times 4. So this is going to be 12 feet per second over the first quarter of a second. Then we're asked, what is the average speed over the next 0.25 seconds? And so for that one, we're going to have that the ball only traveled 1 foot because it went from 3 up to 4. So it went 1 foot in 0.25 seconds. So that is equal to 4 feet per second. Okay, so 4 feet per second in that second time interval. And then part C says, is the height of the ball changing at a constant rate? Well, no, it's not. And how do we know that? Well, if the ball was traveling at a constant rate, we would have constant average speeds, and we don't. Clearly, it went a lot faster in this first quarter second than it did in the second quarter second. Okay, so I hope that helps you with the problem set. And it's a pretty short one. and we'll be back here for lesson 2. All right, good luck.